So welcome all. This is week 8 tutorial for the course Deep Learning from IIT Roper. So I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So the topics that we plan to cover today is vanishing and exploding gradient descent. So what is vanishing and exploding gradient problem? Why does it occur? We are going to discuss about it. Okay, and so then we'll go to different choices of activation function. Then we'll look at unsupervised pre-training. Okay. So this is the broad plan for today, and we'll do some questions related to these topics. I'll try to explain the topic briefly, and then we'll do some questions based on these. So at any point during the content, if you have any doubt, you can either unmute yourself and speak, or you can just post in the chat box. I'm looking at the chats, so both these things works fine for me. Okay. Okay. So yeah. So before looking at vanishing exploding gradient problem, somebody might gone. Okay. So before looking at vanishing exploding gradient problem, we'll just sort of very quickly look at how did we calculated gradient by a back propagation. Okay. So this is a very simple this is sort of a repeat of what we have already done. This is just a simple neural network where you have only one neuron in each hidden layer and you have only one input. Okay. So if you want to calculate the gradient of this loss function is given by y minus hl whole square, that is a squared error loss. Okay. So we want to calculate the gradient with respect to W3, and which is pretty easy, right? So what we have to do is that we have to calculate the gradient of first loss function with respect to HL, then HL with respect to W3. Okay, and further HL is a function of AL. So this again splits into three parts, that is del L by del HL and del HL by del AL and then del AL by del W3. Okay, this is what we have done in past, probably in second or third week. So I'm not going over it again, and we get something of this form. So what I want to highlight over here is that at the end we'll get something of this form. Okay. In this term, there are two important terms that you should see. First term is, okay, yeah. First term is this sigma dash of AL. So sigma is my, let's say, some activation function. Then when we are calculating the gradient, we have derivative of our activation function multiplied with some other terms. Okay. And also we have output of activation function. Okay. So just a very small recap. So what two things you have when you want to calculate the gradient? In multiplication, you have some terms. So let's say these are some terms multiplied with derivative of your activation function multiplied with output of your activation function. Similarly, if you want to calculate the gradient of this loss function with respect to W2, derivative of your loss function with respect to W2, there are, okay, so this thing we already know. So, okay, so there would be something like this also. So this already known that I have written over here will include sigma dash of A2. Okay. So again, similar thing you can observe that you have derivative of your activation function multiplied with the output of your activation function, and these terms get multiplied with each other along with some other terms. Similarly, when I tried calculating the derivative with respect to W1, So there is this derivative of this activation function, and in the end multiplied with the output of the activation function. So you can see, like, if you see this as a tree, or if you see this as a graph, when you have these leaf nodes, right? So when you are ahead in your forward propagation, or when you are early in your back propagation, there are fewer terms that are of form sigma dash that are multiplied with each other. The deeper you go in the back propagation, for example, if you are trying to calculate the derivative with respect to W1, you have more terms of form sigma dash AI, okay, sigma dash AI being multiplied to calculate that gradient, okay. So these are the two things that I wanted to mention. So first is that derivative terms have sigma dash multiplied by some output multiplied by some other terms. So what should the terminology that I should use? So okay, so initial hidden layers. So initial means now that I'm in this region. Okay, so earlier initial hidden layers, and these are the later hidden layers. This is what I'm referring to when I say initial hidden layers. So initial hidden layers have more terms of form sigma dash being multiplied with each other. Okay. So what is vanishing gradient problem? So broadly speaking, so let's see what is vanishing gradient. So if you talk very broadly, so vanishing gradient is the value of gradient that you have obtained is very small. That's why you are not making a lot of progress when you are doing gradient descent method. Okay. So how do you update your weights? Your weight is updated by W minus some eta times gradient of loss function with respect to W. So that this gradient value that you have obtained is so small that you are making negligible improvement. Okay. So this problem is known as vanishing gradient problem. Now, if you look at it from perspective of what we have just discussed few moments ago. So if you have this sigma dash values, like for example, so if you have some activation function for which your gradients are small, okay. So by small, I would mean it would be something, let's say 0.01, or it can be 0.1 also. Okay. So if you have small gradient values and these small values get multiplied with each other, so for the initial layers, the value of gradient would be very, very small. So imagine 0.01 being multiplied by 0.01 10 times. So the value that you would get would be negligible. Okay. Another thing is that because you have this you have this thing multiplied by the value of this activation function. So your activation function value should also be not very small. Okay. Then also it can contribute to vanishing gradient problem. Okay. So there is another similar phenomena which is very similar to vanishing gradient problem, that is known as exploding gradient problem. So what happens in exploding gradient problem is that your gradient values become so large that you miss the optimum point, and whenever you make the update, you are making large updates, and you will miss the like optimal point, and you will exceed that point. Okay. So what are the causes for this gradient being large? When your gradients can be large, so the sigma dash are large. Okay. So for, in this example, let's say your sigma dash over here outputs large values, then if you multiply them together, the multiplication would be, the answer that you will get would be further large. So the sigma dash values would contribute to exploding gradient problem. And the same thing you can also say about this H1, though this won't contribute a lot because this is only one term that gets multiplied in the gradient. But if the output of your function is very, very large, then this can also contribute to exploding gradient problem. Okay. So yeah, so any doubt in exploding gradient and vanishing gradient problem, what are these? And like if you have any doubt in understanding what is exploding gradient problem, what is vanishing gradient problem, you can ask right now. Okay. So now I have told you what is exploding gradient problem and what is vanishing gradient problem. So let's say you are suffering from exploding gradient problem or you are suffering from vanishing gradient problem. What are the possible approaches that you can take? So what you can do is you can change your activation functions. Okay. Suitably. Okay. So this is one solution that you can adopt when you have such problem. Okay. Okay. So there is one more common term that people use when they want to see what kind of activation function they should use and those kind of things. The term is called non-zero centric activation function. Okay. For example, if you look at this sigmoid function, it takes values between 0 to 1, right? And definitely it is not, the values that it takes is not centered around 0. Okay. So the value, the range of this function, the range is 0 to 1. So it won't encounter, this is 0 to 1. Okay. So zero centric function, zero centric activation function are such that they will have both negative and positive values in their range. Okay. So if you have a activation function which only takes positive values or that only takes negative values, those functions would be non-zero centric activation functions. Okay. So there is a small problem that people encounter with these kind of activation functions. Okay. So I'll try to explain what it is. So let's say, look at this particular graph. Okay. And so this is a very simple neural network. And you want to calculate the gradient of your loss function with respect to W1. So this is just gradient of W1 with respect, gradient of L with respect to W1. Okay. So what would be the gradient? So your L is something like, let's say y minus f of, okay, so minus y star whole square. Okay. So this is just your, again, chain rule. So this would be del L by del y. Del y is the final output. Del y by H3, where H3 is your sigma of A3. Okay. And that is right. And then you have del H3 by del A3 and del A3 by del W1. This is very simple chain rule, right? And similarly, you can find your gradient of loss function with respect to W2. Okay, so this is derivative with respect to W2. If you observe these two equations, the first three terms are same in both these equations, right? The only difference is in the last term. right? And if you look at this thing carefully, what is your del A3 by del W1? So A3 is this W1H21 plus W2H22. And what is del A3 by del W1? This del A3 by del W1 is nothing but H21, right? Similarly, this del A3 by del W2 is nothing but H22. Okay. Now let's say if we are using a non-zero centric activation function, then the sign of both my H21 and H22 would be same. Okay. So either both of them would be positive or both of them can be negative. Okay. And these common term that you have, this will definitely have same sign, right? Because these are the same terms, this will have same sign. So what we can infer from this is that your del W1 and del W2 will have same sign. So here we had only two neurons in this particular layer. So if you have, let's say, n neurons in single layer, where your activation function is some non-zero centric activation function, and that is connected to just, let's say, a single output, then all these gradients, right? So then del W1, del W2, and so on, all of them will have same sign. So like if your gradients have same sign, what does this mean? That either all your values in your weight would increase or all your values would decrease, right? So for example, let's say I have centered this graph at point, let's say x comma y. This is the current value of your weight, and you want to move to a optimal point, right? Then the only possible choice where you can move is this gradient, this thing, right? And this thing. You cannot move to these uh, points starting from this point. Okay, like if you have a non-zero centric loss function. So let's say your optimal point lied in this region, you can't reach here. Okay, so this sort of restricts the movement of your weights. So you can't freely update your weights. That's why this is a problem with non-zero centric activation functions. Okay. Any doubt with this thing, like why is having a non-zero centric activation function a problem? You can type in the chat box, or you can even unmute and ask if you have doubt. Okay. Okay. Another thing that is common is something that is known as saturation, and it is most common with this sigmoid type of functions. So what is saturation is, if you see at this graph, right, the value of this activation function after a certain point is very close to 1. It is saturating to some value. And hence what would happen is the gradient in this range, okay, the gradient in this range would be very small. Similarly over here, you can see that the gradient would be very small over here. So this phenomena is known as saturation, and this is a very common problem with this sigmoid activation function. Okay. So this is another thing that I wanted to mention. Now we can begin with different types of activation functions, their advantages and disadvantages. Okay, I'll take some color that is not used here. Probably I can take orange. Okay. So what is the simplest activation function that you can think of? Simplest activation function that you can think of is your linear activation function. Okay. So your linear activation function would look something like this. and its derivative would be just constant 1, right? So what are the disadvantages of, first of all, linear activation function? Okay, the whole motive of going from simpler models to deep neural network was to able to represent non-linear functions. Okay, and if you are just taking linear activations everywhere, then that the sole purpose of going to deep networks was defeated. Okay, that's why this linear function is generally not used in practice, because you can have a lot more explainable methods that are much more explainable, where you can fit in linear curves. Then why go to much more complex models to just fit linear curves? Okay, the next common or useful method activation function that we have is known as sigmoid activation function. You already know about this function. The functions look like something like 1 plus e to the power minus x. Okay, this is logistic activation function or sigmoid activation function. So everywhere this blue curve wherever I have drawn is your function, and this purple one is the derivative of your function. This might not be very much visible, so that's why I'm saying that this is the derivative and this is your function. Okay, so first of all, let's look at the advantages of sigmoid activation function. First advantage is that it is differentiable everywhere, because in deep networks you have to find the derivative in order to compute the gradients and then update the weights. So being differentiable is a desired property for any activation function. So this activation function is differentiable everywhere. Okay, second is that it is normalized between 0 to 1, and hence it is useful for binary classification. Okay, so because it is clamped at 0 and 1, so whatever value we have obtained, we can assign that thing to be the class, and hence it is very useful for binary classification. Okay, so what are the disadvantages of using your sigmoid activation function? So the first disadvantage is, if you look at this thing, as I mentioned few moments ago, this has saturation property, that it saturates on both the ends. Okay, that's why the gradient for a large region is very, very small. So if you look, this is 0 and this is just 0.2. The maximum gradient that it can have is something like 0.25. This is not the exact value, but I'm just telling it, seeing at the graph. Okay, so the gradient, the derivative values that it is obtaining is very, very small, and hence it can encounter vanishing gradient problem. Again, just to get your mind freshened up, so there were many sigma dash terms that were getting multiplied, at least for the weights that belong to the initial layers. Okay, so if you have values that are in range 0.2 or something like that, or even 0.1 for this matter, so 0.1 multiplied 10 times would be a very, very small value, and hence your weight update would be very less. So sigmoid activation function faces this vanishing gradient problem. Second is that it is not a zero-centric function. Okay, so the values that it takes is in range 0 to 1. That's why it is not a zero-centric function. So whatever problem we discussed with zero-centric problem, this also will face. Okay, third thing is that it is computationally expensive. So if you look, you have to calculate exponential, and exponentials are considered computationally expensive. So you have to calculate 1 plus e to the power minus x, which is computationally expensive. Okay. Okay. So to overcome some of the problems of sigmoid activation function, people have tried using something that is known as tan-h activation function. So tan-h activation functions look something like 2 to the power 1 plus e to the power minus 2x minus 1. Okay, this formula you can look anywhere, but this is the main part. This is your function again. Blue one is your function, and purple one is your derivative. Okay, So if you look at the problems that your sigmoid functions have, so the derivative values were very, very less. Okay. But here if you see that for a fairly large portion, you have a higher gradient. Okay. So you can overcome vanishing gradient problem to some extent. But still, if you see this region, again, your gradient are very, very small for these regions. So this overcomes vanishing gradient, but not completely. Okay. Second problem that your sigmoid had was that it was not zero centric. Okay. But if you look at this tan h function, it takes values both negative as well as positive. So this is zero centric. Okay. There is one disadvantage is again this tan h also has exponential term. So this also will suffer from computationally being computationally expensive. Okay. And this is also pretty useful for your binary classification, because this even kinds of saturate to -1 and 1. Any doubt in both these functions that I have discussed? Then I'll go to the next one. Any doubt if you guys have? Okay. So third one is something that is known as ReLU activation function, and this is one of the most used activation function these days. Okay. So the graph of ReLU activation function is pretty easy. I'll redraw the graph because this might be slightly confusing. Okay. So, oh, that's it. Okay. So this is your 0. Okay. For both the axes. So in this graph, this x-axis 0 is here, but your y-axis 0 is here, which is not a very great way of representing, but okay. So your graph looks something like this. Okay. I'll just do something. Yeah. So when you have negative values as input to this ReLU function, this gives 0 output, and when you have positive value, it just returns you the linear x. Okay. So here is the formula for your ReLU activation function. This is max of x comma 0. So if your x is greater than 0, it will output x. If it is less than 0, then it will output 0. And the graph would look something like what I have drawn just now. Okay. So what are the advantages and disadvantages of this kind of activation function? So first advantage is that it is computationally inexpensive. Okay, so you have x, you just check whether it is greater than 0 or less than 0, and you straight away have the answer. Okay, so you need not do any computation on x even. So this is computationally very inexpensive. Second thing is, because if you look at its gradient, so forget about the negative part right now. If you look at the positive part, this is always 1. Okay, so you need not worry about the vanishing gradient problem that we were encountering earlier. Okay. And again, it is useful in regression task or in intermediate layers, because if you have regression task and you choose something like softmax, or you choose something like sigmoid in your last layer, then you won't be able to obtain values, let's say greater than equal to 1 or less than equal to -1. Okay. So in regression, your values can be, let's say 100 or something like that. So for that purpose, your ReLU activation function is pretty much useful for regression tasks. Okay. So what are the disadvantages of your ReLU activation function. Again, this function also is not zero centric. Okay. So again, you will face the same issues that any non-zero centric function would face. So this is one disadvantages. Second problem is known as dying ReLU problem. Okay. So as I mentioned, your gradient is multiplied by the output of your activation function, right? So if the values that you are feeding to your activation function is negative, then your ReLU function always outputs 0. So that makes your gradient 0. Okay. So this is not even about the small updates that we were encountering in vanishing gradient problem. In vanishing gradient problem, what was happening? The updates that were making were very small. Here you won't make any update at all if your x that you are inputting is negative. So this is a big problem with dying with ReLU functions, that it suffers dying ReLU problem. Another problem that it has is that it is not differentiable at 0. If you look carefully, this graph can have this as derivative, this as derivative, or anything between this you can draw as a tangent to at this point. Okay. So this does not have a unique so let's say that it is not differentiable at 0. Okay. People use some approximations to make it completely differentiable, but yeah, it is not differentiable at 0. So it is problematic at 0. Okay. So these were some advantages and disadvantages for ReLU activation function. So to overcome that, what we can do is we can define something that is known as leaky ReLU. So earlier you had at x is equal to 0, you were having value 0, right? Now what you do is you just take a very small a, and for rest of these negative part, what you do is just a second again. For the negative part, you define this to be a of x, where a is very, very small. Okay, so this is alpha of x or a of x. Many people use alpha, many people use a. Okay, so now what you have been able to solve, first problem that you have been able to solve is this dying ReLU problem. Okay, and also you have solved slightly, you have solved the problem of being non-zero centric, because now it can take values less than 0, but the values that it would take less than 0 are very, very small. So you have not solved this non-zero centric problem to a large extent, but you have sort of solved it. And the dying ReLU problem you have taken care of. Okay. So what is one problem that we have with this kind of leaky ReLU thing is that now you have to also find a suitable parameter alpha, okay, that you need to obtain. Okay, so this is another problem that we have encountered by increasing the complexity of your activation function. Okay, last activation function that I'm going to discuss today is known as softmax activation function. This is useful for multi-class classification. So for example, let's say you have to classify your data into 3 classes. So what you can do is, in the output layer you can have 3 nodes, right? And you can use softmax activation. What will it do is, so whatever output you have, it will convert it to a probability. So it will convert it to values between 0 to 1, or a sort of probability distribution. So what does this do is that so phi of zi, so let's say this output layer have output z1, z2, z3, then phi of z1 is your e to the power z1 divided by e to the power z1 plus e to the power z2 plus e to the power z3. And similarly, you can define other phi of zi. Okay, so this is something that is known as softmax activation function. So let's talk about its problem first. So the most important problem that we encountered with softmax activation function is that it is computationally expensive, right? You have to not only calculate the exponential values, but also you have to take the sum of all these values, right? So it is computationally expensive. Now, what are the advantages? So generally it is used as a last layer for multi-class classification. So it is very much useful for multi-class classification, and it converts your values to probability distribution. Okay. Okay. Any doubts related to these activation functions that we have talked? Then we can sort of try attempting questions based on it. Any doubts?
Sir, what is exponential ReLU?
Okay, so I didn't explicitly included it. So the main problem that I talked about with this ReLU thing. So the most important problem that people have tried to tackle is this dying ReLU problem. Okay. So people have suggested, so what people want to do is they want to replace this particular black line with some other very small value. So one option is that you replace it with linear curve. So linear function. Another is that you approximate it with some small exponential function. Okay. So that is something that is known as your exponential ReLU that you just mentioned. That's the only difference. Again, you will have similar advantages and similar disadvantages. Okay. And it would be slightly more computationally expensive as compared to your leaky ReLU. Any other doubt? Okay. So let's look at the questions that I have from previous assignment on this. So first question is, which of the following best describes the concept of saturation in deep learning? Okay. So the options are when the activation function approaches either 0 or 1 and the gradient is close to 0. Second is activation function output is very small and the gradient is close to 0. The activation function output is very large and the gradient is close to 0, and none of the above. So as I mentioned, saturation is that your functions values are very close to each other after some in certain interval. So something like this, your function values are saturated, which leads to the fact that your gradients are very small. Okay. So in this case, if it either approaches 0 or 1, because of which your gradient is close to 0, this is true. Okay. So if your output is very small, okay, and your gradient is approaching to 0, then also it is a saturation problem. Why? Because no matter what value it is approaching, if because of that your gradient is becoming small, that is something that is your saturation problem. And again, even if it is achieving very large function, but it is sort of saturating, because of which your gradient is becoming close to 0, this is also such. So all three options are correct, and none of these is an incorrect option. Okay. So this is asking what is the mathematical expression for the ReLU function. Okay. So this is quite simple. We have just done this. Yeah.
Third one, sir.
Third one is the correct answer. So the next question is, which of the following problems make training a neural network harder while using sigmoid as activation function? So it is asking about the disadvantages of sigmoid activation function. So can you guys think and type like what are the options according to you? We discussed it right now, but yeah. What are the disadvantages of sigmoid among these? Does it face saturation? Is it non-differentiable at 0? So just to recall, sigmoid functions looks something, okay, I'll read it. So it looks something like this, something like computationally expensive range. Okay. So B non-differentiable at 0 is not correct, because if you look at this sigmoid thing, it is very much differentiable at 0. Okay, this is the sigmoid function, right? This is differentiable at 0. So non-differentiable option is ruled out. Okay, saturation is correct because again in this region the function value is getting saturated, in this region function value is getting saturated. This is computationally expensive because you involve exponential. Range of output is again 0 to 1. This is also true. Okay, so three options are correct, one is incorrect. Okay, so next is what are the problems associated with tan h function? So as I mentioned, tan h is sort of an extension of sigmoid function where you make your function to be zero centered. So your tan h is in fact zero centered. So this option is incorrect. It is also computationally expensive because it involves exponential. It suffers less saturation as compared to your sigmoid function, but if you look at its graph, it still suffers saturation in this range, right? So it suffers lesser saturation, but yeah, it does suffer saturation. So you can take this option. Okay, again, this is sort of slightly subjective because it will depend on your application. It is differentiable at 0, so this option is incorrect. Okay. Okay. So what we can do is we can take some 3-4 minutes break, and then we'll go to unsupervised pre-training and other this batch normalization and those kind of things. So we'll start again at let's say 6:50. Okay, so we'll take 2-3 minutes break. We'll start again. Okay, the way you can avoid, see, like whatever disadvantages and advantages I have discussed with that are associated with, let's say, activation function. Let's say this dying ReLU problem or saturation problem or non-zero centric. Those can be avoided only by using some other activation function. Okay, so let's say if your sigmoid suffers from some issue, then you don't use sigmoid over there. Like for your data set, for your specific setting, if you are facing a saturation problem, then you just use some other activation function rather than using that particular activation function. So the way to avoid saturation is to use some other activation. Okay. Okay. So let's look at something that is known as unsupervised pre-training. Okay. So one figure that you might have seen at many places is like whenever people try to draw the what should I say? Okay. So whenever people try to plot the loss of your some deep neural okay, network, it has lot of valleys and lot of local minimas in it. Okay. So pre-training can be very useful in guiding your network or model to converge at right place. Okay. So for example, in 2D, if you have some graph like this, okay, okay. So if somebody starts from here, there is a possibility that that person would land up here, will see that my gradient is 0 and would be stuck over here only. And he has not achieved the global minima, but he'll be sort of satisfied. So the model that he'll learn might not be very effective. Okay. If he starts from here, he might land up here. Okay. Again, if he starts from here, he'll land up here. So this region might face some kind of overfitting. Okay. This might be your optimal region. And this might be just your local minima that you are stuck and you are not able to exit out of it. Okay. So initializing your model sometimes becomes very important. So one initialization that was suggested is known as unsupervised pre-training. So what is the idea behind unsupervised pre-training is that let's say you want to initialize this particular layer, weights associated with this particular layer. So you want to initialize these weights, okay, these orange weights, all these weights, okay. So the idea is that this layer should should be a good representation of your previous layer. Okay. So if you are initializing from a point where your current, this particular layer, for example, let's say, is a good representation of your previous layer, then this can be like very exciting, right? That it is able to represent your previous layer very well. So that's why you are initializing your model to that particular way. Okay. So one way to do that, for example, in using autoencoder is that first of all, what you do is you just look at a small portion of your network. Okay. So you just take these three. So you want to initialize the weights over here, this yellow shaded part that I'm shading. You want to initialize these weights. So you will just take these two layers. So this red box layer, you will just take these two layers. Okay. And you will model this as an autoencoder that we did in previous weeks. Okay. So this is your input X. What you want is you want some X hat. This would be your X hat would be your output. You want your X to be equal to X hat. You want to have this H1 so that your X is equal to X hat. Okay. So your loss function would be nothing but X minus X hat, right? So this was your objective function for your autoencoder. And the same is over here also. Okay. What we are trying to do is we want to find these weights such that We want to find these weights such that this H1 representation that you have got is a good representation. So why I'm saying that it is a good representation? I am saying it because you are able to reconstruct your X from your H1. Okay, that's why this is a good representation. After you have constructed your H1, you take the next block. Okay, so you have obtained your H1 and you have obtained your these weights. Okay, so then you take these two layers. Okay, so you give H1 as the input, right? And then you train your these second weights. So I'll highlight it again by yellow. You train these weights so that it is able to find a good representation of H2 now. Okay, so you want to have minimum loss between H1 and H1 cap. Okay, so this is your loss. So in this way, you can initialize all your weights up to this point. Okay, and after you have initialized your weights, then you can use your data that is available with you. Just remember that till this point, we are calling it as unsupervised pre-training. The reason is you haven't used the y values that are available with you. You are just using the x values. Okay. Now, after you have initialized, right, now you will use your y values to fine tune your weights. Okay. So there are two advantages that you will get by using this kind of algorithm. First is because you have sort of good representation in every layer. So the point that you are starting from leads to a better and faster optimization. Okay. Second thing is that this also helps you in some sort of regularization. Okay. Why I am saying this is, okay, so this alone won't help you in regularization, but if you take this kind of initialization, okay, and when you are fine tuning your model, at that point, if you like take very simple steps also to regularize, for example, if you just take L2 regularization, then you won't be able to move very far from this representation. Okay, so you won't be able to move very far from a setup where you have intermediate layers have good representation. Okay, so in this way, it helps you even regularize your model. Okay, so there are two advantages of this pre-training. It helps you in better optimization, and implicitly it helps you also in some sort of regularization. Okay. Any doubt in what we have discussed till now? I hope the basic idea behind how we pre-train this model is clear. Okay. We can solve some questions based on it. Okay, so the question is, you have to choose the incorrect option related to unsupervised pre-training. I would request you to please type it in the chat box. So whatever option you think is incorrect. Okay, let's see what other have to say, then we'll confirm. Okay. So first option says autoencoder can be used to learn representation from the input. This is correct, right? We are learning intermediate representation, which are correct. So this option is correct. We converge faster to a minima using unsupervised pre-training. This is also correct, right? I just said that we'll have better optimization, better convergence rate. Okay. Hidden layers used in feed-forward neural networks are initialized with random weights. This is incorrect. Why? Because the whole purpose of unsupervised pre-training is to initialize it with some weights following some particular conditions. What is that condition? Condition is that the intermediate layers that we are getting are good representations. Okay, so this option is incorrect. They are not initialized with some random weights, but they are initialized weights based on some rule, and that rule is that the intermediate representations are good representations, or we are able to reconstruct back the vectors. Okay, that is the rule that we have to follow. So they are not some random weights, but they follow some rule. Okay. Okay, here is the next question. Can you please tell me which options are correct? Which of the following are advantages of using unsupervised pre-training in deep learning? Okay, somebody says B and C. What others have to say? Somebody says B, C, and D. Okay. Okay, let's look at all options one by one. Okay. So, few moments ago only, I mentioned that it has two advantages. First is better optimization. And second one is some sort of implicit regularization. Okay. So if it is doing some sort of implicit regularization, then it will also help you reduce overfitting, right? If you are able to regularize your model, then it will help you reduce overfitting, correct? So A option is also correct, that no one of you picked. So A option is correct. Okay. Second option says pre-training models converges faster. This is obvious, most of you have said that. Okay. Third option says it improves the accuracy of your model. Right, if you are not overfitting and if you are able to converge faster, then this would lead to you getting better accuracy in your model, right? So this option is also correct. Now last option says it requires fewer computational resource. Now if you look at the method carefully, that it is a two-step thing now, right? The step one is your pre-training. That will also require you to do everything. It will require you to have gradients, optimize your weights, right? And that too in several steps. One for your first layer, once for your first layer, again for your second layer, and so on. This is step one. And step two is fine tuning or your normal training. Okay. So if you look at it, it is not computationally cheaper, but computationally much more expensive than normal initialization, right? Because you have to train model even for initializing your weights. Okay. So it does not require fewer computational resource. In fact, it requires more computational resource. Okay. So last option is not correct. First three options are correct. Okay. Okay. We'll talk more about initialization only. Okay. So I won't go into details of these things. Most of these things were displayed by the professor using experiment. I have just picked the crux out of it and I have tried to write it down. Okay. So there are few possible options for initialization. We'll see if we initialize in that way, what possible issues can we encounter, and right, or like if there are some methods of initialization that has some advantages. So we'll see to it. Okay. So the first option is that you initialize all your weights and biases to 0. Okay. Now, if I say weights, you implicitly assume that I'm also talking about biases. Okay. So if we initialize all our weights to 0, okay, So the problem that you, yeah, somebody has to say something. Okay. Okay. So the problem that you might encounter is that all the weights in your layer 2 would remain same. Okay. Throughout the training. Okay. So if you have, let's say this is this as input, this is your second layer. Okay. And you have initialized all your weights to 0. Okay. So what is the value that you would enter in this particular, okay, so I'll highlight it. So what is the value that would be the input to this particular neuron? It would be 0, right? Because all the weights are 0. So all the inputs are 0. Okay. So if you have same activation for this layer, then all the outputs are also the same, right? Let's say the function outputs, for example, sigmoid, it outputs 0.5. So all the outputs are same. Okay. So when you will do back propagation, the update that you will have for all these uh, weights would be same. Okay. For that reason, all the weights in your layer 2, so connecting layer 1 and layer 2, would remain same throughout your training. Okay. So this problem is also known as symmetry breaking problem. Okay. Where your all the weights in your layer 2 remain same. Okay. Second problem is, even if you don't initialize your all the weights to 0, but you initialize your weights to some same value. For example, let's say you take all these weights to be 1 throughout. Then also you will suffer from same problem, that is known as symmetry breaking problem, where all the weights in this layer will remain same. Okay. So this is another problem. Okay, so we have talked about assigning all the weights to be 0 or all the weights to be same. These two didn't work out well. So what is the next option that we can have? The next option that we have is, let's have some random weights, because all the weights being same didn't work. Let's try assigning them random weights. Okay. So now you have two options. You can either assign random small weights, or you can have some sufficiently large weight. Okay. So if you assign random small weights, okay, then your activations are close to 0. Okay. The reason is, if you have small weights, then your sigma wi xi, this is the input to neuron, right? So these values would be small, right? And hence your activation values would be small. And as you remember, in the gradient we have last term, so the term hi in multiplication, I mentioned it in the beginning of today's class, that you have this thing being multiplied. That would mean that your gradient that you are obtaining are close to 0. Okay. That's why you would encounter vanishing gradient problem. Okay. So if you take random small weights, you will encounter vanishing gradient problem. Okay. Now, the second thing is, if you take large weights, okay, and you take some functions like sigmoid, for let's say you are doing some classification task, and you take large weights for that, okay, then your sigma wi xi will output large values. Okay. And for large values, your activation function is saturated. Okay. Again, because of saturation, your gradient would be close to 0, and you would encounter something that is known as vanishing gradient problem. Okay. So now what to do? You can't initialize same values, you can't initialize 0 values, you can't initialize small random weights, you can't initialize large random weights. So there is a way to go through it. So for sigmoid and tanh activation function, if you sample weights from your standard normal distribution and you scale it by the factor 1 by root n, okay, right, I think it is 1 by root n only, yeah. Then, okay, yeah. So you have to sample using this, then you would be able to obtain good result. So this is the initialization that you can take. For ReLU, people have experimentally shown that z by 2 root n works better. Again, this z is your standard normal distribution. Okay. So these are few things that like if you just theoretically read, you might not understand or you might forget it tomorrow. So the best way would be to train a model using these different kinds of initialization and then see how your output varies, how your accuracy is varying. So you can try these things and then you will have a much better understanding of what is happening and why it is happening might not be there, understanding might not be there, but yeah, you will get to see the kind of pattern that it is following. Okay. Okay. So there is one very small last thing that is left. This is something that is known as batch normalization. I'm not going to go into very detailed discussion about this thing. So what is batch normalization? So let's say you have a data set D and you split it into three batches, D1, D2 and D3. Okay. Now, how do you go about when you do, let's say, batch gradient descent? So what you do is you first train on your dataset D1, then you train on your D2, and then you train on your D3. Okay. Now let's say for some layer, let's say some hidden layer L, okay, there is a possibility that the let's say the representation that you get in layer L. Okay, just one more thing. So what I mean by representation in layer L is, let's say you have this kind of network. Okay, I'll just make it slightly more formal. Okay, then this is your input, right? Let's say your input was 1, 2, 3. Then you will get some output over here. Let's say this is 3, 4. So this 3, 4 that you got is some representation of your input. This is just what I mean. So if I mean that layer L representation is just the outputs of all your L layer neurons. That is your layer L representation. Okay. So let's say the layer L representation follows some distribution, right? It would be from some distribution. So for D1, let's say that distribution is this curly D1, and for D2, your distribution is some curly D2. Okay. And there is a possibility, because you are randomly sampling D1 and D2, that this D1 and D2 are not same. Okay. So this would cause a problem. Why would it cause a problem is that you have fitted your layer or all the weight so that you are able to produce D1, and now you want to change everything and you want to fit it to your D2. And again, next time when you will encounter your D1 data set, there will be a lot of change in your, there will be a lot of distribution shift. Okay. So to overcome this, what we can do is, for every layer, we can convert this distribution to standard normal distribution. So how do you convert any distribution to standard normal distribution? You just take, let's say this is your x, you take the mean of x and divide it by your standard deviation. Okay. So this is what it is happening. Okay. So S is your ith layer representation. So this is the output that you would obtain in S. So Sik, for example, here this is S21, this is S22. Okay. This is how this formula is written. So what it is saying is that for every layer, you just take the expected value and divide it by your variance. And k is your, okay, so this k would vary from for your data points. So over all the data points that you encounter, you just take the mean values in that particular layer, divided by your variance, and you have normalized. Okay. Why is it called batch normalization and not just normalization? Because you are normalizing just for one particular batch. Okay. So what you have done is, for every output, you have converted it to standard normal distribution. Okay. And in this process, one more thing that happened is that because you were normalizing this layer, so you were converting this to standard normal, you are converting this to standard normal. Now every layer within a network, so within a batch also, is following same distribution. What you wanted is, you wanted, let's say this is layer 1, this is layer 2, this is layer 3. You wanted layer 1 for batch 1 to follow same distribution as layer 1 of batch 2. But now all the layers, layer 1, layer 2, layer 3 of batch 1 also is following the same distribution. This is the extra byproduct that we have got. Okay. So this is what is batch normalization. So this is just similar to what you have been doing, normal deep neural network. But after every layer, you will just batch normalize this thing. Okay. Okay. So let's try a couple of questions that is there on this batch normalization and this unsupervised pre-training. So can you please read the question and try to answer? And if you have any doubt also, you can ask. So the first question is, what is the main cause of symmetric breaking problem in deep learning? Okay. Yeah. So D option is correct, as somebody answered. This happens because of equal initialization of weight. Or other option people can give you is zero initialization of weight. Okay. What is the purpose of batch normalization in deep learning? So as I mentioned, it ensures that the distribution of different, so across batches, you want your distribution to be same. As a byproduct, what you get is that distribution of different layers are also same. Okay. So here also your option D is only correct, that it ensures that the distribution of different inputs at different layers is same. Doesn't change, means same. Okay.